So we're going to continue our discussion of numeric methods for approximating integrals, for approximating the area under a curve. So far, we've looked at the midpoint method, the midpoint rule, the trapezoid rule, and of course the left and right Riemann sums from first semester calculus. We've got one more to talk about. It's what's called Simpson's rule. And I'm working with the same function here that we've had in the previous lectures. This is y equals x squared. And of course, if you remember in the trapezoid rule, instead of using rectangles to approximate the areas, we use trapezoids. Because trapezoids, they more closely fit along the curve up here than rectangles do. Well, kind of continuing this reasoning, well, are there curves that fit even more closely? Well, yeah, we could use an actual curve, for example, and that's what Simpson's rule does. Simpson's rule says, well, look, instead of fitting things with straight lines, which clearly aren't going to perfectly match something that's curved, let's try fitting parabolas instead. Right, so what Simpson's rule does is it works with the points in groups of three, right? Because it takes 3 points to uniquely determine a parabola. So Simpson's rule says, look, take these 3 points, find the equation of the parabola between them, add up the area, and we can find the area of a parabola, right? We can find that exactly using the power rule. It's our standard integration methods. Add up those areas and see what you get, right? That's going to be your approximation, right? Now, if you do that, right, this is the formula that you come up with. This starts off with all the same wording we've seen before, right? We're going to start off with if f is a defined integrable function. So obviously, if it's not integrable, we can't do this at all. And we have this interval that we're going to be integrating it over. And we do have an additional requirement that we haven't seen before. First, the number of partitions has to be even, right? So our n has to be greater than or equal to 2, and it has to be an even number. All right, then Simpson's rule says the area, that's the integral here, is again approximately equal to, you know, the pattern that we come up with here. It's the first point and the last point, and the ones in the middle alternate 4 times, 2 times, 4 times, 2 times, etc. So we have to have this pattern. We have to have the sums. It has to start with 4 times and end with 4 times. Right. So this is going to require an odd number of endpoints, which is why the number of intervals has to be even. And we've got all the same setups down here. Delta x is b minus a over n, and this is just how those x sub k's are defined. All right, so let's see how we can actually do this. We're going to do the same thing we did before. We're going to use 4 intervals. That's greater than 2, and it's even, so that's a fair ball. Right, and then we're going to, again, just as we've done in the previous example, so we have a basis for comparison of these methods, we're going to find the area under y equals x squared. So what are our x values? Well, those are the endpoints of the interval, 0, 1, 2, 3, and 4. And what are the function values? Well, 0 squared is 0, 1 squared is 1, 4, 9, and 16. All right, so what does Simpson's rule say? It says the area is approximately equal to, it's going to be f of x 0 plus 4f of x1 plus 2f of x2 plus 4f of x3 plus f of x4 times delta x. And if you look back, I didn't mention this explicitly, but if you look back at the definition there, it's delta x divided by 3, right? Not the 2's that we've seen before. Okay, so let's put the numbers in here. And I really want to put the numbers in and see what this comes out to. This is 0 plus 4 times 1 is 4. 2 times 4 is 8. 9 times 4 is 36 plus 16. Delta x is b minus a over n. That's 4 minus 0 over 4, which is 1. So it's just times what? I always forget that 1/3, right? Times 1 divided by 3. And what do we get here? 12, 48, 58, 64. This is 64 divided by 3. And if you figure out the exact area, right, we know how to do this. This is x cubed over 3 from 0 to 4. Put 0 in there, obviously you're going to get 0. 4 cubed is 64 thirds. And look at that. Simpsons Rule, Simpson's method gave us the exact answer. If you think about it for a minute, we're going to talk more about bounds on the error you get from these methods in the next lecture. But if you think about it, that actually kind of makes sense, right? Because what did we do here? Well, we were approximating a parabola with parabolas. Yeah, okay. I mean, it intuitively kind of makes sense that you really should be getting a perfect match here. Right, so let's the next slide here. This summarizes the results that we've seen in all of these methods. Right, the left and right Riemann sums gave us 14 and 29, which were not very good. Right, really not very good at all. But for the same number of intervals, the midpoint rule gave us 21, which was really pretty good. That was only a third off. The trapezoid rule was good, but not as good. That was off by 2/3. And of course, we saw with Simpsons rule, that gave us the exact result. So those are all the different methods that we're going to talk about. So in the next lecture, what we're going to look at are some formulas for putting an upper bound on the error for each of these methods. Obviously, we can't calculate the error exactly. If we knew exactly what the error was, we could just add it to our approximation and get the exact value and we'd be done, right? So we aren't going to be able to do that, but what we will be able to do is put an upper bound on the error, which is a useful thing to do because in a practical situation, you'll see when we look at the formulas, that's going to give us a way to determine the number of intervals that we have to use to get a specific level of accuracy.